Welcome back. In this video, we discuss an example of a quadratic surface, and the first example in lesson 6 of a concrete surface that we can graph. In this case, we're going to look at a class of surfaces known as ellipsoids. This is one type of a quadratic surface, and it comes from generalizations of ellipses in R3. When we look at ellipsoids, the general equation for an ellipsoid is very similar as the general equation for an ellipse in R2, except that we add a third dimension. So in this case, we would say that an ellipse would be x minus h squared divided by a squared is the x component of the ellipse equation. And then we have y minus k squared divided by b squared. And then could you guess what the third component is? Sorry, I'm using a new pen, and I should really look like a 2. There it is. And then the third component would look like z minus m squared divided by c squared. And then we set this equal to 1 in the general case. And notice this is very similar to the equation for ellipses in R2, except that we have a new component. When we look at this equation, we have a few really important parameters here. We say that this equation gives an ellipsoid centered at the point in R3, h, k, m, which are inside the squares in the numerators of these fractions. And then the denominators of each fraction represent the lengths of the corresponding semi-axes. So here we say that A is the length of the x semi-axis. B, of course, is the length of the y semi-axis. And then the new piece of information for ellipsoids in R3 is that C is the length of the z semi-axis. Well, this is great in general. Let's sink our teeth into a specific example and see how to graph this. The example we're going to look at is to graph the ellipsoid defined by the equation x squared divided by 9 plus y squared divided by 16 plus z squared divided by 25 equal 1. And the first thing that we're going to do as we go to graph this is use our brain, not to boot up Mathematica on our computer. In particular, let's put this in general form by specifically identifying the center, which we said was going to be h, k, m. When we look at the center, in this case, there is no shift happening in either the x, y, or z component, and thus we conclude immediately that the center should be at 0, 0, 0. We can also see that the length of the semi-axis are given by the square roots of the denominator. We can see this by rewriting our equation x squared divided by 3 squared plus y squared divided by 4 squared plus z squared divided by 5 squared. And maybe we want to put this into the general form of an implicit equation where the right-hand side is equal to 0 and the left-hand side is an expression just in terms of x, y, and z, which we would call f of x, y, and z. And the reason that we might do that is that then we get this specific reference to the idea that this is an implicit equation where the output variable z is not written in terms of the two inputs explicitly. Recall from our first discussion of quadratic surfaces, before we start actually working with software, we want to use our brains and do 3 things. analyze the valid input and output, or the domain and range if it's a function, analyze the x, y, and z intercepts on the coordinate axis, and then also look at specific traces to give us intuition. Let's start with the first one of these, which was to analyze valid input and output. We really are looking for what limitations do we have on x, y, and z. To start this process, notice that we can do the same type of thing that we did earlier in lesson 5 videos, which was to simplify our work and look only along each axis. So suppose that we set 0 equal to y and z, which would immediately imply that the only variable non-zero would be x, and then on the bottom we have 3 squared. Here we have minus 1 equal to 0. We can do a little bit of work, which comes from our knowledge and dexterity in algebra, to say that this is actually equal to x squared is equal to 3 squared, which of course we could call was 9. And then we could cancel out these different parameters here. How do you undo a square? Take the square root, and then this would be the square root of 9. We had this discussion. The square root of a square, this is quite subtle, is equal to the absolute value of x, and then we have, this would be 3. When we solve this equation, we have that at that particular line, this is going to be negative 3 or x equal 3. And this actually gives us the intercept. So we're actually doing two things at once. We see that there are two x intercepts. One of them is at negative 3, 0, 0. And the other one is at 3, 0, 0. And these are called x-intercepts, where the ellipsoid passes through the x-axis. But it also says something else. When we look at x squared over 3 squared equal to 1, so I just brought the 1 over to the other side from that general equation, this actually gives a limit on valid x inputs. And in particular, we see, because this must be equal to 1, in this case, x can never be equal to 3. Right? Or the absolute value of x can never be equal or greater than 3. And if we looked at the original equation, if we looked at the case where we had x squared over 9 plus y squared over 16 plus z squared over 25 equal 1. Sometimes when we're not directly on the y equals 0 or z equals 0 planes, the x's might not be exactly 3. The only where the x's are 3 or negative 3 are at the intercepts, but we see that x could never be greater than 3. If x is greater than 3 or negative 3, less than negative 3, this ratio will be bigger than 1. These are going to be non-negative numbers, which means this would be violated. And in particular, we get this limit that x will always be less than or equal to 3. Right? So this was a way to start. We looked at what happens along the 0, and then we said to ourselves, oh yeah, by the way, we know that that is actually the outer limit. And this actually leads to the conclusion that not only must x be less than or equal to 3, so too y must be less than or equal to 4, because here on the top, when I square 4, I would get 16, and that ratio would be 1, and that forces these to be 0. And then finally, we see that z can never be bigger than 5 in magnitude on this ellipsoid. What we've just seen is when we graph this particular ellipsoid in Mathematica, we should create a viewing window that includes all these valid outputs. Let's do that. We'll switch over to Mathematica. Remember, since we have this surface being graphed by a general form f of xyz equals 0, this is an implicit equation, which means we're going to use the contour plot 3D command. Here we go over to Mathematica to get our first insight on what this surface might look like. Boom! Here we are in Mathematica. We're going to go ahead and graph our surface. We begin by the hair on our chinny chin chin. We have some concept of what we're going to do here. I noticed that when I was working with a student in class, some students are doing this thing where they open and close the brackets immediately within each other. I do not recommend that. I recommend separating these and then lining up the first letter of contour with the actual end bracket here. And the reason is this makes debugging really easy. You'll see me doing this in all the videos. Debugging means when you have an issue with your code, how do you find that issue? And then when you write the individual lines of your contour plot inside, actually separate those lines individually. So here we had that this was going to be x squared. Let's go ahead and make a general form. So this is x minus h squared, and then we'll take the entire thing and divide it by a squared. And up top here, we're going to go ahead and define, let's say that we had h was equal to 0, which is what was the case here. K was equal to 0. And then we also had that m was equal to 0. These were the coordinates of the center point. And then we had the length of the semi-axis. We said that a was 3. We said that b was 4 in this case. And we said c was 5. So that's the specific example that we were working on. The definition of the general form of the ellipse was to have 3 of these, and then maybe we want to put it in general form. We'll subtract 1 and set it double equal to 0, comma. Here this would be y minus k divided by b squared, and this is z minus m divided by c squared. For those of you that are not familiar with how I got that writing, you can always use the basic math assistant to do this. So one way, of course, is to go into the calculator and then use the exponentiation thing. And then for fractions, you would just hit this thing. You see it? I did the same things on my keyboard, and you can see if you just scroll over this, do you see how that thing says superscript control 6? So I literally hit control and then hit 6 on my keyboard. And then if I wanted to do division, do you see how it tells me to do a fraction on the keyboard? Push control entry. And this gives you some insight in how you use your keyboard to get these commands on the screen. Now that I've written the definition of this equation, I can determine for contour plot what the x, y, and z values were. Remember in my analysis, I needed this to be a minimum of 5 because the z values were limited between 5 and -5. So I'm going to go ahead and be more conservative and go from 8 to -8 here in the x. And then I'll go ahead and copy this. I guess I could just rewrite it each time. So this would be y from -8 to 8. And then the same thing's true in z from -8 to 8. Oh, I broke a cardinal rule. Every time I open a brace, immediately close that brace. Z from -8 to 8. Notice that when we're coding, I'm partitioning each line separately. Okay, let's go ahead and enter this command. So I'm going to hold shift and push enter. Look at that. So that's an ellipsoid. And notice it is a three-dimensional version of an ellipse. You could think about it like a very smooth football. Because I have issues, I cannot just leave it like this. I like to make it look kind of different than the way Mathematica makes it look individually. I like to go for blue. I don't know why. Opacity. Yeah, and let's go to 20% opacity so it's kind of see-through. And then the mesh actually messes me up a little bit. So let's go ahead and turn the mesh off. You'll see me do this over and over and over again. And I evaluate it. Yeah, when you turn the mesh off, it kind of looks like a two-dimensional surface. So you have to be a little bit careful on this. We can turn it back on by just saying true. Right. And then we could also put the origin in the middle. So if we say axis, origin, I'm going to tell Mathematica where I want that origin. I'm going to say that it's 0, 0, 0. Okay, so now we've got that ellipse. And then if we do this, we might turn the mesh back off and see what happens. You can kind of see that there's a ellipse or an egg-shaped thing here. And what's really cool about this is we actually did in our paper and pencil analysis, we actually saw where some of the points along the axis were. So here I'm going to go ahead and do a graphics command. So I'm going to do show. Notice that my end brace of show is lined up with the first part of show, and then I've indented inside, so it's super easy for me to read. This is a coding technique to really make finding errors easy. So I'm going to do a graphics 3D command, and then in this case I'm going to do a point, and the point that I'm going to want, well, we've just said that the x intercept, so we'll say x left is going to be equal to -3, 0, 0. So that's the left x-intercept. And the right x-intercept, reading right to left, would be 3, 0, 0. Oops, I broke my cardinal rule again. Every time I open a brace, immediately close the brace so that I have no issues with braces. So now we're going to go point size. I think we've determined that 0.008 is a really good point size. And then the points that we're going to graph, they're going to be 2 of them. So we'll say let's do x left, and we'll also graph x right. We evaluate. Looks like that's not quite big enough. There we go. So those are the 2 x intercepts. See them? Or maybe we turn the mesh to true. I don't know. Kind of ugly, right? All right. By the same analysis, my claim is that you could say, I'm going to get annoyed having to type left and right, so I might just do L and R, and then just make sure to update this code over here, L and R. I could do the exact same analysis via pen and paper, and I encourage you to do that at home to find that the left and right y intercepts are at -4 and 4, and I just set x equal to 0 and set y equal to 0. So this would be 0, 4, 0. And we could go ahead and graph those points. So let's go ahead and graph those. This is y, L, and y, lowercase y, capital R. Okay, so now that gives me the bounds on the x and y. And then finally, you could guess that the upper and lower bounds on my output, so I might call this z lower bound, and then perhaps you call it z upper bound. So the upper bound would be, or the lower bound would be at -5 in the z coordinate, and the upper bound would be at 5, because when we do that solution in the same way that we did for the x values, we would have that this is z lower and z upper, and we get the top and the bottom there. And all of a sudden we have kind of the intersection of the ellipsoid with the different axes. Let's switch back over to our pen and paper and start looking at what traces are, and then we'll come back to this example at the very end of this video to actually graph some traces to see what they look like. Here we go. Welcome back to the handwriting part of this. We had talked about, in general, when finding the graphs of quadratic surfaces, we start with our mind and then use computers. In the first step, we looked at the valid input and output. We actually did some analysis to confirm in the first step that the x-intercepts for this ellipsoid were positive and -3 in the x component, and then 0 and 0 in the y component. We made a claim in the Mathematica portion that the y-intercepts were positive and -4 in the y and 0 in the x and z, and that the z-intercepts were 0, 0, positive, -5. Let's go ahead and confirm this. Z-intercept would imply that this is happening on the z-axis, which means that x is 0 and y is 0. And this would mean that if we looked at the equation, the x component and the y component would disappear, and we would just have z squared divided by 5 squared minus 1 equals 0. And indeed, we see by the same type of analysis that this would mean that z squared is equal to 5 squared, and then we could do the same square root inverse that we had talked about. This is going to be the absolute value of z, and this is going to be 5. And then, of course, we had that x was 0 and y was 0, so this is now corresponding to 2 zeros in the first component, and then we know the solution is either positive or negative 5. So indeed, we've confirmed using that mathematical analysis that the component, at least here, was checked. This one was checked. Viewers at home, I encourage you to do y. Never trust your teacher, right? You got to do the math for yourself. Remember that the third step of this analysis was to look at traces. And we said that one of the best ways to do this was to start with the most popular traces if appropriate. So the xy trace was the intersection of the xy plane given by the equation z equals 0 and the surface given by original equation. If we set z equal to 0 in our surface equation, we're left with something that looks like x squared divided by 3 squared plus y squared divided by 4 squared minus 1 equal to 0. And this is an ellipse in x and y. This is actually a pure ellipse in x and y embedded in R3. And I'll show you what I mean by this. Remember that we could actually create a vector valued function here for this ellipse. And that vector valued function, we said we were going to have a times the cosine of theta. You're going to have to go back and look at your notes from lesson 5 to remind yourself how this works. So in this case, we said that the general vector valued equation for an ellipse was to take a times the cosine of theta and then add h to it. We said that the y component would be b times the sine of theta, and we would add k to that. And then the z component, well, in this case, the reason we have a z component is because we've said this has to lie in the plane z equals 0. So this ellipse is an ellipse in x and y, so the vector valued function we can use to describe that should be in x and y, but it has a third component. In other words, it's embedded in R3. We can now graph this trace. Perhaps we use the parameter t as 3. I don't even want to use 3 for now. All I want to do is the general version, and you'll see why I do this in the code in Mathematica. So this would be cosine of t plus h. This would be b times the sine of t plus k, and this would be 0. And then for you viewers at home that want to see this written out, of course this would be 3 cosine of t. H is 0, so that's not an issue. This is 4 times the sine of t, and this would be 0. So what we just stated here was that when we look at this trace, which is the intersection of the ellipse and the plane z equals 0, that trace is going to be a curve which sketches a ellipse in R3, and this ellipse is given by this vector valued function. Remember, in this vector value function, we can use parametric plot to graph this. Command. Let's do the other two traces by hand, and then we'll finalize the work that we're doing here in Mathematica to actually show all 3 traces. So I believe that we talked about the xz trace next. And the xz trace came from intersecting the y equals 0 plane, which of course we call that the xz plane, hint hint, with the surface. If we set y equals 0, this of course would look like x squared divided by 3 squared plus y goes away, and now this is z squared divided by 5 squared, And we now see that this is minus 1 equals 0. That's by the defining characteristics. And of course, now this is an ellipse embedded on R3 in x and z. Well, we have the same vector valued function, and maybe we call this vector valued function R2 of t. This vector valued function is going to have a component in the first slot. So this would be a times cosine of t plus h. We have nothing in the second slot because the y equals 0. And the third slot we're going to treat as if it was the second component of an ellipse. So in this case, instead of b times sine of t plus k, we would have c. We would have the length of the z semi-axis, and then we would shift it by m, which is the center point along z. Of course, we can do this specifically for these values. So this would be 3 cosine of t. So this is centered at 0. We have no shift. And this would be 5 sine of t. I'm going to let the viewers at home figure out what the YZ trace is. And I would pause the video before you see me switch over to Mathematica so that you yourself can get a sense of what vector valued equation we're going to use to define the third trace. Let's switch over to Mathematica and actually visualize these traces on the curve. Here we're in Mathematica. We had our ellipsoid that we defined up here in general terms, and then we had the points that defined the x and y intercepts. Now we want to graph traces. To do so, we had vector valued functions, which in Mathematica are plotted using parametric plot, and we're going to use parametric plot 3D. So here I'm going to go ahead and define parametric plot 3D. And then remember, we had 3 different traces. I guess I can open and close this and say this is going to be end parametric plot 3D command. Okay, so here was the first trace that we said. This was going to be a times the cosine of t plus h. The second command was going to be b times the sine of t plus k, and then for the x, y trace, the z was going to be 0. If we want the entire ellipse, we're going to go 2 pi radians, or 360 degrees. So we'll let t range from 0 to 2. And then this is cool. If I push the escape button and then type the word pi and push escape again, Mathematica will turn that into pi. Okay, so now we have this thing. This should be an ellipse on the x, y plane. Here we go. Okay, there it is. You see it? Let's go ahead and create the x. Let's go ahead and first of all, let's do plot style here. So plot style, and then maybe we do directive. And let's do 2 things. Let's turn this to bright red, and we'll thicken it a little. Let's do thicker than a Snicker, shall we? So here we go, 0.008. Okay, so there's the trace, and we could actually visualize this trace by further combining the xy plane here. So let's do contour plot 3D, and then here we'll look at the xy plane. So let's go ahead and define the xy plane as z equals 0. There's the implicit equation for that. And then we need the same values. Do you see how this is kind of redundant to have the exact same thing here? I could change that, but I'm not going to. Here we'll use the contour style, so I'm just going to copy and paste, and we'll call this thing red, and we'll use opacity. And then let's turn the mesh off of this, just so that we're not confused. So here, mesh is false. Okay. Do you see that? That the trace is the intersection between the xy plane and the ellipsoid? It's pretty cool, right? Notice that traces are in R3. They're curves in R3, parametric curves. Let's go ahead and switch over to the XZ trace. And what we said in the XZ trace, so I literally just copied the two parametric plot 3D and contour plot 3D. We said that the XZ plane had a y coordinate of 0, and it had a z coordinate c times sine of t plus m. And then instead of doing red, maybe let's do green, just to make it look different. And then here, the equation for this one, we would have y equals 0, since it's the xz plane. And then we'll do also green on this one. So literally, it's the same two commands. It's just done with different equations. Oh, Mathematica is complaining. Do you see that the comma at the end? The end of a show should not have a comma. So this thing, that's why it was complaining. Okay, there it is. Do you see that trace? Yeah, do you see why I'm trying to have you do Mathematica? Could you imagine doing this by hand? Oh my God. Pretty powerful, right? All right, I'm going to go ahead and graph the YZ trace, and I'm going to do it just by copying these two parametric plots. For viewers at home, I want to be very clear that what I'm showing you is not the best way to code this in Mathematica, but it is modularized, which is really nice. You break it into different pieces. So here I'm going to go ahead and answer the question that I posed to you earlier. We've used orange, red, we've used red, green, and blue. Maybe we'll use purple or orange. Let's try orange. Okay, so there's orange. And then this is going to be the x equals 0 plane. And we'll do orange here. Okay, so there's our three traces. Orange is not quite great, is it? We could try yellow. Yeah, let's try yellow here. Okay, that's a little better. Okay, the reason that I wanted to show you this was, this is gonna, I hope this makes you smile as much as it makes me smile. Let's go ahead and move around the center, shall we? So let's go 1 in the x, -2 in the y, and then maybe, I don't know, 3 in the z. So, what's going on here? What did I not do? Oh, of course, my traces are going to be different in this case because my center's off. So, sugar, I was hoping that I really could make this happen for you. Well, certainly we can move around. The one thing that I want to say immediately, you could move around these, so you could make the x semi-axis length 1, maybe you make the y semi-axis length 6, and the z semi-axis length 2, and that will give you a different ellipse. The intercepts are making me angry, so I'm going to go ahead and just comment this. Yeah, this is my angry voice, by the way. So here we go. So there's no intercepts there, but you see we can move around the ellipse a bit, right? And you still get the same traces. Anyways, this gives you an introduction to how to graph traces and also what an ellipsoid is, which is a generalization of an ellipse. In the next video, we'll get into the second type of quadratic surface, which is called an elliptic paraboloid. See you there.